6 continents separated by vast expanses of water. This is the familiar image of our planet that we have all shared since childhood. But the Earth has not always looked like this. Over the past 4.6 billion years, our planet has gone through many geological eras. During some of these eras, almost the entire surface was covered with ice, while in other periods, on the contrary, the polar caps melted completely. In the distant past, the continents were not arranged as they are today. Land blocks moved relative to each other, resulting in movement, collision of continents, and the emergence of supercontinents that united almost all of the land masses. About 335 million years ago, there was only one supercontinent, consisting of a large part of the Earth's surface. This continent was called Pangea, which means the whole Earth in Greek, or all the lands in Greek. Later, about 200 million years ago, this huge landmass began to fracture through the movement of tectonic plates and separate into the continents as we know them today. To think of all the continents coming together like a puzzle is incredible. It's also incredible that earthquakes and plate tectonics could have pushed so much land together to create the world we know today. Life at the time of Pangea was different than it is today. The climate was warmer and drier. The life of animals and plants was completely different. Most animals suffered a mass extinction. Amphibians tried to adapt to the new conditions in different ways. Some increased their size, or on the contrary, decreased it. Others acquired denser, shell-like coverings to better retain valuable moisture for the body. Unusual animals have appeared. As for the flora, ferns, lycopods, and horsetails have almost disappeared. But plants more resistant to drought, such as conifers, have spread. Pangea then looked like a mystical world where the Earth seemed to have existed forever, and where animals and plants lived in places we could not even imagine. Dear traveler, good morning. Today we will travel through time to the time of the last supercontinent the Earth has known. Before leaving to explore a unique and mysterious world, think of liking the video and subscribing to the channel to not miss anything. Thank you, and have a nice trip! The word Pangea comes from the Greek words pan, meaning all, and Gaea, meaning earth, which means all the lands. This name perfectly refers to the supercontinent, because in the past Pangea was only one land, since all the lands were then gathered in one place. A supercontinent is a continent composed of most or all of the Earth's landmass. The most recent supercontinent to include all of Earth's major landmasses, and arguably the most famous, was Pangea. Supercontinents have sporadically joined and broken up over the course of Earth's geologic history. Recall that the geologic history of the Earth is a sequence of events in the development of the Earth as a planet. These events include the formation of rocks, the emergence and destruction of landforms, the rise and fall of the seas, ice ages, and the appearance and disappearance of species of living beings. The most modern definition emphasizes that the supercontinent is a geological formation that, with its structure, affects the distribution of heat flows, air masses of the Earth, etc. It is a large structure, but it does not necessarily unite all the continental blocks. In the distant past, all the continents formed a single whole, the supercontinent Pangea. This huge continent began to form around 335 million years ago, during the Paleozoic period. Many geological, paleontological, paleoclimatic, and geodetic data that exist today can be considered as strong evidence that the continents were once adjacent and then separated from each other. Between them, ocean basins opened up, but they were nevertheless once part of a single planetary structure on a gigantic scale, Pangea. During the process of formation of Pangea from older continents, mountain systems appeared in the places of their collision. Some of them still exist today. For example, the Urals or the Appalachians. These early mountains are much older than the relatively young mountain systems such as the Alps in Europe, the Cordillera in North America, the Andes in South America, or the Himalayas in Asia. Due to erosion over millions of years, the Urals and the Appalachians are now low mountains. Most of this supercontinent was concentrated in the southern hemisphere. The only ocean that surrounded it was called Panthalassa. Life during Pangea was different from today. The climate was warmer, and the fauna and flora were completely different. Pangea split about 150 to 220 million years ago into two continents. The northern continent of Laurasia then split into Eurasia and North America, while the southern continent of Gondwana then gave rise to Africa, South America, India, Australia, and Antarctica. Supercontinents existed earlier. For example, Rodinia, which disintegrated about 750 million years ago. And according to some predictions, in the future, the continents will reunite into a supercontinent called Pangea Ultima in about 250 million years, when Africa, America, and Eurasia will collide. Since the 17th century, scientists have been trying to explain the origin of our planet, as well as its characteristic topography. In this context, the famous English physicist Robert Hooke, a zealous rival of Newton, drawing attention to the fact that the remains of marine animals were found far from the sea, concluded that the contours of the seas and lands had changed repeatedly throughout the history of the Earth. But by the beginning of the 20th century, most geographers believed that the ratio of seas to continents had remained unchanged since antiquity. The relief of the planet would have changed only because its entrails gradually cooled and it contracted unevenly. Others thought that mountains were born from the accumulation of sedimentary rocks. Science is grateful to the German meteorologist and astronomer Alfred Wegener for the various justifications of two fundamental geological ideas. First, for the idea of continental drift, and secondly, for the hypothesis that in the distant past of our planet, all the present continents could have formed a single giant supercontinent, Pangea. According to Wegener, it all started during his stay at the University of Marburg in 1910, when his roommate received the latest edition of the Earth Color Atlas for Christmas. The idea of moving continents first occurred to Wegener when, while studying the world map, he was struck by the similarity of the coastlines on both sides of the Atlantic Ocean. In the fall of 1911, Wegener had become aware of paleontological data on the past land coherence between Brazil and Africa, of which he had known nothing before. This had led him to analyze the results of relevant geological and paleontological studies on this question. After studying these data, he was convinced of the fundamental correctness of his idea. Inspired by his unusual concept, the 31-year-old Wegener dared to present it on January 6, 1912, at the Congress of the German Geological Association in Frankfurt am Main. Wegener explained that the continents had not always been where we saw them on the map. Throughout the history of our planet, they had changed position. Nevertheless, the hypothesis of continental drift was not received positively by the fixist ideas on the genesis of the Earth's relief, and it was strongly criticized. The very idea that parts of the Earth's crust, including the continents, could move on the surface of the planet seemed absurd to them. It contradicted everything that science knew at the time. The scientific community greeted Wegener's theory with hostility, judging him inexperienced, unfamiliar even with the well-known developments of his predecessors, and rejected his hypothesis as attempting to go against the apparently already perfectly functional and dominant paradigm of fixism. The theory convincingly explained a number of events in the history of our planet, but in fact, it was poorly argued. Wegener failed to explain what forces could move entire continents. The proponents of this theory assumed that the continents were the remains of the Earth's oldest crust, which would have arisen as a result of the melting of the bowels of the early Earth's history. These remains were then supposed to be firmly fixed in certain areas of the planet, and the Earth's crust was considered to be capable only of vertical movements, downwards forming the ocean bed, or upwards generating the continents and mountains. Horizontal movements were admitted, but considered very minor. In the same framework, it was thought that the main driver of change was the internal heat of the Earth that was cooling. In addition, they considered that the respectable geological circles on both sides of the Atlantic, and particularly in North America, did not show any coherence. In any case, the idea was considered unsupported by facts and mechanically implausible. For a long time, its role in the sphere of interest of the majority of geologists was therefore negligible. Convinced by his idea, which would provide a new perspective on the geological history of the planet, Wegener did not abandon the work he had begun. His pursuit was facilitated not only by his perseverance, but also by the fact that critics still had not bothered to seriously analyze Wegener's arguments for a new viewpoint. Thus, the author of the hypothesis began a methodical and comprehensive search for data that could bring even more clarity to the problem that interested him. As a result of all his research work, the book, The Origin of Continents and Oceans, was published in 1915, containing not only the new concept itself, but also its solid and versatile justification. After that, it was no longer obvious to ignore the innovative hypothesis. And despite the general unfavorable situation associated with the pressure of the fixist paradigm, serious researchers interested in the continental drift hypothesis began to make themselves known. The most important contribution to the popularization of his theory was made by the British geologist Arthur Holmes. He suggested that powerful convective flows of matter in the depths of the Earth could be the driving force behind the continents. Hot masses would slowly rise from the planet's interior, while cooler rocks would gradually sink deeper. The South African Alexander Logé du Toit, one of the world's greatest field geologists, became Wegener's main disciple at this time. Certainly, accepting the concept of continental drift and drawing on his own experience, du Toit began to advocate the idea that in the distant past there was not one continuous supercontinent Pangea, but two supercontinents, Laurasia and Gondwanaland, separated by the ancient ocean Tethys. It was then that the ideas of the Austrian geologist Eduard Suess, such as the ancient ocean Tethys and the ancient continent Gondwana, which included Central and Southern Africa, Madagascar, and the peninsula of India, proved useful. However, the later idea of Gondwana itself also began to refer to South America, Australia, and Antarctica, and thus to this supercontinent. In turn, the term Laurasia referred to a single hypothetical ancient supercontinent of North America and Eurasia. Later, it was realized that mid-ocean ridges extended across the globe, and in 1953, American physicists Maurice Ewing and Bruce Heezen discovered that trenches extended along submarine ridges into deep faults in the Earth's crust. A few years later, another American scientist, Harry Hess, suggested that the mid-ridge system was a zone where new oceanic crust was constantly being born. Hot magma rushes through the faults to the surface, pushing aside sections of the seafloor on either side of the trench. Thus, the main driving force of global plate tectonics had been discovered. Since the mid-1960s, Wegener's hypothesis has finally gained acceptance in the scientific community, becoming the basis of modern geography. The positive change in the interest of the scientific community of the time in Wegener's concept was due to the fact that the author of the hypothesis had managed to gather a whole series of arguments in support of it. The geological evidence for continental drift attracted attention because of the very strange similarity between the Atlantic coasts of South America and Africa, as well as because of the compatibility of the relief folds of one continent with the relief folds of another, as if they were lines from a torn text. The evidence also showed a similarity of geological sections on opposite continents. Meanwhile, a glance at the world map showed that there was an as-yet undiscussed but very interesting possibility in the reconstruction of Pangea. On a world map, we can see that the Iberian Peninsula, where Spain and Portugal are today, is very consistent in size and shape with the Gulf of Mexico. In addition, we can see that the Florida Peninsula that covers the bay, judging by the map, is surprisingly well coordinated with the Bay of Biscay in Europe. Also, it is edifying to note that deposits of rare heavy metals such as ilmenite, rutile, zircon, and monazite are exploited off the coast of Florida, in the Gulf of Mexico, and across the Atlantic Ocean, but also off the Iberian Peninsula. In addition, paleontological evidence has explained the phenomenon of Paleozoic and Mesozoic distribution of the same species of plants and animals on opposite continents, apparently completely separated by ocean waters. The new proposal proved to be very important in this regard because the old explanation of the Fixus geologists did not suit the fauna and flora biologists of ancient times. The historical proximity of these particular parts of the planet is also supported by the data of biology and paleontology. For example, the mystery of eels strangely leaving European rivers to swim 6,000 kilometers, or 3,700 miles, to the Sargasso Sea, located just above the Florida Peninsula, to spawn, has long been discussed. It may just be an atavism. 130 million years ago, eels were able to spawn in the Sargasso Sea region when the continents were closer together. Eels settled in Europe, even in the region of the British Isles, which means that in ancient times, the same Bay of Biscay should have been close not to the northern part of the eastern North American continent, but to its southern part. This is also demonstrated by the history of horseshoe crabs, nicknamed horseshoe crabs. Today, these horseshoe crabs can only be caught in the Sargasso Sea and the Gulf of Mexico. However, it is curious that judging from the horseshoe crab distribution zones stand in the Moscow Zoological Museum, horseshoe crab fossils are also found in the British Isles area. This again means that it seems that Northern Europe was located somewhere very close to the Bay of Mexico. The author of the new hypothesis also used paleoclimatic data, which was only a secondary area of interest for the meteorologist Wegener. These data also confirmed his position. They made it possible to determine the position of the continents through their membership in paleoclimatic zones and traces of glaciation. And yet, all these arguments and evidence have not been considered by the geological community as decisive and sufficient. After all, the mechanism for generating such continental drift was not yet clearly established. Subsequently, after the death of Alfred Wegener in 1930 during an expedition to the Greenland ice sheet, the drift hypothesis began to gradually lose its supporters. Opponents also actively worked to discredit it, attacking Wegener with criticism that is now unanswerable, especially because of his unsuccessful explanation of the cause of the drift. As a result, the hypothesis has faded into obscurity to such an extent that mobilism has been taken out of the realm of official science and thus eliminated from the curricula of academic studies. However, as is usually the case, the rejected idea did not disappear completely. It was recalled again in the active search for terrestrial magnetism that took place after World War II, as well as with the intensive sounding of the ocean floor using echolocation. All this evidence then emphasized that in ancient times the Iberian Peninsula was located in the embrace of the Gulf of Mexico. New arguments necessary to test and develop the hypothesis were retained, and theories in favor of the hypothesis were developed. It turned out that the entire Earth's crust was divided into large separate parts, called plates. It is not the continents themselves that are moving, but the plates to which the continents are firmly attached. The driving force of this movement is explained by convective heat flows of the Earth's mantle material, i.e., its gigantic circulations. Thus, since the beginning of the 1960s, Wegener's hypothesis, enriched with new arguments, has experienced a real renaissance. It is now called plate tectonics. As we know today, the Earth's crust is composed of 7 large plates and a number of small lithospheric plates covering its entire surface. They move, collide, move apart, cling to each other's edges, or dive under each other. When 2 oceanic plates, or oceanic and continental plates, collide, a subduction zone is formed. The edge of one plate plunges into the depths of the other plate and melts completely to a depth of about 100 kilometers, or 60 miles, where temperatures of 1,000 to 1,500 degrees Celsius, or more than 2,730 degrees Fahrenheit, prevail. A chain of volcanic mountains forms along the edge of the other plate. Deep-sea trenches are often found in subduction zones. An example of this phenomenon is the Mariana Trench, which arose when the Philippine and Pacific plates collided. Also, when 2 continental plates collide, high mountain systems are formed, such as the Alps or the Himalayas. The Himalayas were formed when the Indo-Australian plate collided with the Eurasian plate, which happened about 40 million years ago. India is now moving northward at a rate of 5 centimeters per year, and so the Himalayas continue to grow. Often, the plates do not collide head-on, but slide side by side, clinging to the edges. The resulting tension is discharged in the form of earthquakes, sometimes very powerful. For example, in the California region, where the North American plate slides along the Pacific, and as a result of such seismic activity, the San Andreas Fault was formed. With the advent of global plate tectonics, the view of the evolution of our planet has changed dramatically. It is no wonder that this theory is put on a par with Darwin's theory of evolution and Einstein's theory of relativity. But is it really so perfect? In recent years, the already classical view of the movement of the lithospheric plates is gradually evolving as knowledge increases. This is why plate tectonics appears as a kind of self-regulating mechanism in which all the systems that make up our planet participate. We know, for example, that mountains have a very great influence on the Earth's climate. But now, it is becoming clear that the climate also affects the tectonic processes that take place in its depths. One example is the Andes, a mountain system that arose where the oceanic Nazca Plate is subducted beneath the South American Plate. In the southern part of the Andes, the climate is humid, which contributes to the development of erosion processes. As a result, a large amount of sedimentary deposits penetrate into the Pacific Ocean, which helps to reduce the impact of the plates. In the northern and central parts of the Andes, the climate is dry. Almost no sedimentary deposits form here, so the oceanic plate literally scrapes the edge of the continent. The frictional force of the plates here is so great that the Andean mountain system along the coast rises higher and higher. As a result, rain clouds have less and less chance of breaking through this wall that has risen in their path. Scientists continue to debate why the lithospheric plates are moving. There is much ambiguity on this issue, just as there was in Wegener's day. Most believe that the main driving force is slow convection currents, which occur due to heat transfer between the Earth's molten core and its mantle, But this explanation does not fit well with a picture of tectonic movements that we observe. Another cinder is located on the other side of the globe, under the Pacific Plate, which is gradually decreasing in size. Thus, Wegener's idea marked the beginning of a great revolution in our vision of the nature of the Earth. This revolution is not over. It continues slowly. Scientists still face two fundamental questions about the supercontinent of Pangea. How and why did our supercontinent form? But also, why did it split into several parts? The answers to these questions are not so obvious. Scientists still do not agree on a single version of the course of events. Several valid theories are in competition. Modern modeling of this ancient time in the Earth's geological history has shown that the assembly of Pangea, like supercontinents in the distant past, even occurred more than once. About 800 million years after the beginning of the decomposition of the previous supercontinent, a new supercontinent was formed, and all the events of the genesis were repeated. Thus, Pangea is the supercontinent closest to us in time. In the space of less than a century, the model explaining the formation of Pangea has been modified several times. If Wegener reconstructed the northern part of Pangea, or Laurasia, assuming that the northeastern corner of North America, or the Labrador Peninsula, was once included in the trough of the Bay of Biscay, the modern reconstruction is different and not very intelligible compared to the reconstruction of the southern part of Pangea, or Gondwana land. Most researchers think that everything is in the Earth's mantle. Probably, the tectonic plates were moving because of the heating of the mantle due to radioactive decay, which caused the formation of Pangea, and then its breakup into separate continents. Such processes do not occur constantly, which is why it took so long for the supercontinents to form and break up. Isn't it amazing that the power of the Earth's mantle could have so affected the appearance of our planet as we know it today? About 150 million years ago, Pangea broke up completely. But what fractured this large landmass? Did the continent become a victim of its gigantic size, which broke it up? About 120 million years ago, the huge continent in the southern hemisphere, Gondwana land, also broke up. How did this happen? Triggered by convection currents of deep heat of the planet, the continents moved to the surface. Pangea split, and the strong adhesion of the continents ceased. Imagine a film on the surface of a hot beverage. It will be the continental plates above the planetary matter, boiling in a continuous current as old as the Earth itself. Many experts believe that the appearance of Pangea upset the balance of masses on the planet. This imbalance even affected the rotation of the Earth. The lithospheric cluster eventually broke up into two large chunks, Gondwana land and Laurasia, which in turn also began to disintegrate. This has happened more than once in the history of the Earth. Other supercontinents that appeared long before Pangea had a similar fate. This is the case of Rodinia, an ancient supercontinent whose time of formation is still debated, although scientists believe it existed about 1 billion years ago and began breaking up 750 million years ago. The Pangea fault lines likely crossed areas of lithospheric plates, weakened by collisions with other plates, such as areas where a huge island or another continent was once linked to a continent. The split occurred in such a way that Gondwanaland united South America, India, Australia, Africa, and Antarctica. Laurasia then included the present territories of Asia, Europe, Greenland, and North America. At the site of the split of its two edges, the Atlantic Ocean began to expand gradually, as oceanic crust was added in the area of the Mid-Atlantic Ridge, and Africa moved away from South America. India broke away from Africa, leaving behind a piece, Madagascar, and headed towards Asia. Thus, Asia shrank into gigantic folds that we call the Himalayas. On satellite photographs, the edge of the continental plate seems to have been crushed. You can even feel how the colossal pressure pushed Everest up. From space, the mountains look like they were created as easily as the folds of a tablecloth. On the other hand, the tectonic approach between Africa and Europe caused the formation of the Alps. To explain this fragmentation, scientists do not agree. Indeed, some are convinced that the main role in the breakup of the continents was not played by the tectonic processes that caused the stretching and cracking of the Earth's crust. Geologists have long paid attention to the island ridge in the central Pacific Ocean, where the Hawaiian Islands are located. Here, a chain of volcanoes stretches for nearly 3,500 kilometers, or more than 2,000 miles. The youngest of them, Mauna Loa and Kilauea, still spew lava. The most distant and oldest of these volcanoes was active more than 40 million years ago. All these volcanoes were generated by the so-called hotspot. This is an outpouring of magma, where a flow of hot material rises from the deep layers of the mantle and digs a hole in the lithosphere. This is where the volcano comes in. The hotspot is generally considered to be stationary in the mantle, while the lithosphere moves slowly above it. As a result, the volcano gradually moves away from the magma chamber and dies out. But next to it, a new volcano arises, just as on a sheet of paper, which is slowly driven over a lit candle. A chain of brown spots appears. Thus, a chain of volcanoes of different ages has formed along the Hawaiian submarine ridge. The liquid lava flows quietly from the Hawaiian volcanoes, without destructive explosions and without danger. It spreads around the crater and quietly solidifies, now crumbling into many angular blocks, now hanging with a smooth black crust. Yet these volcanoes were not always so quiet. There have been hotter periods in Earth's history. Scientists have discovered layers of frozen lava, a kilometer thick. Their surface area exceeds the size of the Scandinavian peninsula. Obviously, the volcanoes here have not calmed down for several million years. The reason for these powerful eruptions is thought to have been caused by mantle jets of unprecedented strength, sliding easily through the lithosphere. But what could give rise to these giant jets? Apparently, areas of anomalous heating. At the bottom of the oceans, the Earth's crust is very thin, only a dozen kilometers or so, Hot rocks lying just underneath heat up this thin envelope to make their way to the surface. But under the continents, the thickness of the crust reaches 30 to 80 kilometers. Such a shield reliably protects against the heat in the Earth's bowels. However, if the continent reaches certain critical dimensions, an abnormally large amount of heat accumulates under it. As a result, a hot jet of material rises from the mantle, but cannot rise again. The lithosphere does not conduct heat well, and is therefore a thermal insulator. Then the molten substance spreads to the sides. A horizontal convective flow is formed. At the same time, glowing rocks come out of the Earth's bowels. This powerful current crosses the upper layer of the lithosphere, and after undermining the thickness of the continent, it tears it apart and pours out at the surface. Prolonged volcanic eruptions begin. If this hypothesis is correct, then along the line at which the continent separates, many volcanoes appear. Traces of ancient eruptions have undoubtedly been preserved along part of the Atlantic coast of Africa, South America, and Europe, where the fissure that divided Pangea was located. In fact, along these shores of the Atlantic Ocean, there are vast layers of basalt, which appeared precisely at the time when Pangea was gradually breaking into two fragments. However, the facts collected so far are too few to favor one of the two hypotheses. The same hypotheses can also explain the collapse of Gondwana. It is the largest continent ever located in the southern hemisphere of the Earth, which included Africa, Australia, South America, Antarctica, India, and Madagascar. It is since about 160 million years ago that Gondwana and Laurasia began to divide into continents that are familiar to us, leaving between them spaces that became new oceans, the Atlantic, Indian, and Arctic. The map of the Earth gradually acquired its known aspect. It is during the Paleozoic period that Pangea became a single supercontinent. The duration of existence of this supercontinent is about 290 million years. This period was marked by the emergence of various living organisms and ended with their mass extinction. All the rocks formed during this period are attributed to the Paleozoic group. As this supercontinent slowly separated along the rift, the sea periodically intruded into the developing rift valleys. By the end of this process, the physical world was transformed, with a new geographic redistribution of the continents having important consequences for both climate and the course of biological evolution. The circulation of water in the oceans, known as the main mechanism of heat transfer from one region of the Earth's surface to another, radically changed life on our planet because of the redistribution of the continents. The newly formed ocean basins became barriers to the spread of plant and animal life, especially for land dwellers, but this change also affected marine organisms. The breakup and collapse of Pangea was so critical in the formation of our modern world, affecting everything from the distribution of animal life to our current climate, that it needs to be examined in more detail. At the end of the Paleozoic era, a portion of the ocean surrounding the Earth intruded into Pangea westward into the region we now call the Mediterranean Sea. Eventually, this water invasion spread further west, splitting Pangea and separating Europe and Africa. The resulting latitudinal basin became a sea of its own, known to geologists as the Tethys Ocean. Its formation had a significant impact on global climate, as it allowed latitudinal ocean currents to flow through it. The process of tearing the continental crust moved even further west, separating South America from North and Central America. Seawater periodically flooded them early in their development, then evaporated. Salt deposits formed. These Triassic evaporites are found today along the northwestern edge of Africa and in many parts of Europe. There is evidence that at the end of the Paleozoic era, the climate was extremely dry, especially in the interior of the Pangea continent. Some of this data is given to us by the fauna and flora preserved in fossil remains and by sedimentary rocks. Researchers believe that the central parts of the supercontinent were very arid because rainfall was very rare. This desert climate was due to the fact that these territories were surrounded by high mountains, which held back the influx of rain clouds in some areas. In addition, the abundance of sandstone and petrified sand dunes are a telling feature. In today's world, sand dunes characterize hot, dry desert conditions. There is no reason to believe that this was not the case in the past. Sandstones can form in many different types of natural environments, but it is generally easy to distinguish between those that were once sand dunes and those that were deposited along sand beaches or in rivers. For example, large grains and cobbles are not easily transported by the wind, so sand dunes are characterized by small grains that are deposited much more uniformly than coastal or river sands. In addition, the layered structure, which reflects the actual sequence of sedimentation, is very different in these two cases. But if dune deposits were quite common in the Permian, they are not the only evidence of a dry climate. This era is distinguished by evaporite strata, or salt deposits, formed under conditions where seawater basins are isolated from the open ocean and simply dry out, leaving behind only salt deposits that have been dissolved there. Like sand dunes, evaporite deposits indicate a warm, dry climate. There is disagreement among geologists as to the significance of the facts we have just considered for understanding global climate in the Paleozoic. Pangea was crossed by the equator, and many of the evaporite and dune deposits came from low latitudes. Perhaps the climate at that time was not so hot, and their predominance is only the result of geographical location. But the vast continental mass of Pangea had a dry climate in the interior, with extreme temperature fluctuations of hot summers and cold winters. However, thanks to the discovery of coal deposits in some places, scientists have come to the conclusion that the part of Pangea's territory closest to the equator was covered with tropical rainforests. It is difficult to imagine how different the climate was on this prehistoric supercontinent. Therefore, unlike the available data, one should be cautious in their interpretation. It is not easy to reconstruct with great accuracy the details of the Earth's climate a 250 million years ago. But whatever the details, we know that the continents moved slowly and that the collapse of Pangea took a long time. The influence of this very large landmass on climate continued through much of the Mesozoic. Prehistoric fossils help scientists understand what life was like at the time of Pangea, about 300 million years ago. At the beginning of the Permian, the last period of the Paleozoic, primitive mammals were already living on lands abundantly covered with forests. It was at this time that reptiles began to emerge and multiply rapidly. It turns out that it is only possible to find these fossil remains for one simple reason. All the continents once formed one land and were not separated by the waters of the oceans. Cynognathus was a reptile that lived on our planet during the Triassic period, when Pangea existed. Scientists have discovered the remains of this animal in South America and Africa. The remains of Lystrosaurus, another land reptile, have been found in India as well as in Antarctica and Africa. If these lands were not part of a single Pangea, the discovery of prehistoric Lystrosaurus remains in places so far apart would simply be impossible. Paleontological evidence clearly indicates the validity of the theory of the existence and division of Pangea. Many species of animals lived on Pangea, and most of them were very different from modern fauna. For example, the Traversodontidae were a family of herbivores that were thought to be the ancestors of today's mammals, and during the time of Pangea, they were particularly numerous. During the Triassic period, the first archosaurs, including the famous fossil Archaeopteryx, appeared on Earth and eventually became the ancestors of modern crocodiles and birds. At the end of the Triassic period, as mentioned earlier, dinosaurs also inhabited our planet. However, these new dinosaurs didn't look quite like the ones in Jurassic Park. Researchers believe that these dinosaurs had very porous bones that were covered in feathers, not scales like the reptiles we are familiar with. Most of the living organisms at that time inhabited the seas. Organisms flooded every possible habitat, capturing freshwater bodies and shallow waters. Herbivore organisms, such as tabulae or corals, which are animals with a calcareous skeleton, also archaeocetes, recognized as sea sponges, and bryozoans, which are microscopic animals living in colonies with a wide variety of shapes. During this period, many classes and types of living beings appeared. At the very beginning, all living organisms lived in the seas, and the most developed of them were fish, many species of corals, and trilobites, marine arthropods, which lived exclusively in the Paleozoic. Amphibians were less numerous and remained mostly in the water. Most of the species that lived on Earth during the existence of the supercontinent of Pangea became the ancestors of the modern fauna. More advanced plants appeared during the time of Pangea. Indeed, the diversity of plants of different colors explodes. Fertilization is no longer linked to the presence of liquid water. Dissemination has become an important factor. Pollen can travel thousands of kilometers to fertilize a female gamete. Seeds are transported by wind. Animals and even water allow species to conquer new territories. Palynological data on spores and pollens indicate a decimation of gymnosperms, the naked seed plants represented today by conifers, and their replacement, especially in the northern hemisphere, by lycopsids, which are today small spindly plants resembling mosses. During the Paleozoic, plants could be much larger. The genus Pluramea, extinct plants, was strongly represented. Many fossil specimens have been found in Russia, Europe, China, and Australia. Their leafless stems reach 2 to 3 meters. The dominant place of lycopsid and fern spores indicates a survival strategy. In the southern hemisphere of Pangea, the Permian flora was essentially composed of Glossopteris, extinct ferns with seeds that could be arborescent. The fossil specimens found are leaves from 2 to 30 centimeters long, or a maximum of 12 inches. After the mass extinction of the Permian-Triassic crisis, it was replaced by the Dacroidium flora, which was of the same type. However, there is mostly a dearth of fossilized plants and the absence of charcoal. A strong growth of organic walled microfossils is noted. These have been interpreted as fossils of fungi that participated in the decomposition of plants. In other words, the continents would have carried a large mass of decaying plants. Today, the ginkgo biloba is the only remaining species of the order Ginkgols, whose beginnings coincide with those of Permian, about 280 million years ago. The ginkgo biloba tree can reach 40 meters in height and live for over 1,000 years. The leaves of this living fossil are widely used in herbal medicines. Already inhabited by bizarre life forms, dinosaur prototypes, sharks and reptiles of enormous size, it was at the end of the Permian period that the largest extinction in Earth's history occurred. A mass extinction occurred about 252 million years ago. This period is called the Permian Mass Extinction. As a result of this mass extinction, among the survivors were creatures that became relatives of modern birds. The first species of dinosaurs also appeared at the same time. By the end of the Permian period, according to the latest estimates of scientists, 93 to 97% of all sea dwellers and nearly 2/3 of land animals and plants had disappeared. The main reason given for this is a terrible catastrophe 250 million years ago, which virtually destroyed the ancient great forests and subsequently caused the greatest mass extinction of all time. Nevertheless, this remains one of the greatest mysteries for paleontologists. According to many scientists, the extinction of most of the planet's biomass is the result of the formation of the supercontinent Pangea. In a study led by Chinese scientists, the authors report that researchers around the world have now accumulated a sufficient body of evidence to explain the severe climate changes on Earth 250 million years ago. Among the main indicators, a sharp decrease in oxygen saturation in the global ocean and an increase in the concentration of greenhouse gases in the atmosphere, such as carbon dioxide and methane. As a result of the intense acid rain, the chemical composition of the seawater has changed, causing corals to disappear. At the same time, as a result of global warming, the chemical composition of the Earth was changed, and it gradually turned into a lifeless desert. The cataclysm drags on for millennia, and the climate pendulum swings one way or the other. Periods of warming are replaced by a cold wave. According to this hypothesis, the source of all the troubles lay in the large-scale movement of tectonic plates that occurred 50 million years before the beginning of the recorded cataclysms. During collisions, part of the plate sank into the mantle, which was accompanied by a thickening of the Earth's crust and an increase in the depth of the world ocean. It was then, at the beginning of the Permian, about 300 million years ago, that these geological processes caused the reversal of the Earth's magnetic field, when the planet's magnetic poles reversed. More importantly, a large amount of cold material found its way into the mantle, where a sort of plume was formed. For millions of years, due to thermal convection, some of the material in this plume has been brought to the surface. This happened for the first time 251 million years ago on the territory of modern Siberia, when the lava covered more than 4 million square kilometers of the Earth, a huge area corresponding to 7 times the size of France. In addition, another similar hole in the Earth's crust was formed 260 million years ago in southern modern China. It is these 2 eruptions that occurred as a result of the massive convergence of tectonic plates that Chinese scientists call the source of all evil, in the form of greenhouse gases and acid rain that hit the planet even before the appearance of dinosaurs. It should be noted that not all scientists agree with their Chinese colleagues. The most criticized time gap is 50 million years between the formation of Pangea and the volcanic eruptions. Some scientists believe that the reasons must be sought chronologically, closer to the extinction itself. Thus, the most important consequence of the formation and disintegration of Pangea was the mass extinction, which led to changes in the Earth's population, with the emergence of various new species of plants and animals in the next era. What if Pangea had not broken up? If we correlate the current appearance of the Earth with its image from the time of the dinosaurs, it would be difficult to find similarities. The countries would be completely different. Many of them would have a different geographical location, therefore a different climate. For example, Siberia could be in the subtropical zone and be similar to California today. Not only the position of the countries and their climate would change, but also the fauna. If Pangea had not broken up, the Earth would now be inhabited by other species of animals that are unknown to us and whose diversity we can only imagine. Moreover, a single continent implies an ease of movement. Land transport would become even more popular, since any area of Pangea could be reached by land. Air travel would certainly become even faster and more convenient. The absence of maritime borders would make any political conflict more dangerous. The conditions for starting a war would be simplified because troop movements would be faster. But who says that the human species could have evolved so quickly? And more simply, could the human species have been born if the supercontinent had not broken up? The merging of continents is a cyclical process. According to the Wilson cycle, it seems that supercontinents form in cycles, coming together and breaking apart through plate tectonics every 400 to 500 million years. This means that one day Pangea will become a reality. But the continents are progressing towards each other so slowly that unfortunately we are not destined to see exactly what the consequences of their unification into a single supercontinent will be. We can only guess and build various theories about it. With the advancement of scientific work, researchers are more and more convinced that deepening paleogeographic research and restoring the appearance of the Earth of the past with the greatest precision is of major importance. This research is advancing because the more detailed the past reconstructions of our planet are, the more accurate the predictions of the future evolution of the Earth will be. Before Pangea, there were other supercontinents. Pangea itself was assembled from older continents, but this was no more than a brief episode of unification, and before and after, fragmented pieces of land were separated for a long time by seas and oceans. The ancient landmasses were sewn together by tectonic evolution, like crazy patchwork. The material of the ancient continents was always used in the same way to form the supercontinents, only it was cut differently than on today's atlases. In the past, the first continents were separated by oceans, but gradually, as the continents converged into one land, the oceans closed and a supercontinent was formed. Recall that according to the existing theory of continental drift, the formation of a supercontinent from the association of existing continents is a cyclical process that repeats itself every 500 million years. It is estimated that half of the time since the continents changed location has already passed. This means that in about 250 million years, the Earth will change again. A hypothetical next Pangea, called Ultima, will appear, which will include Africa, Australia, Eurasia, the Americas, and Antarctica. Perhaps one day, all the current continents will converge on the territory occupied by the Pacific Ocean, and, as has already happened in the history of the Earth, they will form a supercontinent, so that later, with time, when it splits into separate parts, they will start again in the opposite direction. The next cycle of movement of the continents will begin. Already now, you can see that the Red Sea Rift is opening. Africa is moving closer to Eurasia at a rate of 3 to 4 centimeters per year, or 1 inch per year. Therefore, the Mediterranean Sea is gradually closing. The Atlantic Ocean expands, the Pacific Ocean shrinks. The Indian Plate is moving northward, and like an iron is crisscrossing the Eurasian Plate, which also leads to the growth of the Tibetan Plateau. All modern observations are based on paleomagnetic data on the speed and direction of movement. Satellite geodesy, or GPS geodesy, makes it possible to reliably determine which plate is moving in which direction and at what speed. Therefore, the existing models and assumptions have a physical justification. This is not fiction, but long-term observations of plate movement. According to these models, in about 30 million years, the Japanese island arc will join the Russian Far East coast. On the geological timescale, it is possible that an internal sea basin will first open within the Eurasian continent, and then it is possible that the Siberian and Amur plates will separate again, and an ocean basin will open between them. In 250 million years, the North American continent will rotate counterclockwise, and Alaska will be in the subtropical belt. Eurasia will continue to rotate clockwise, and the British Isles will be at the North Pole, while Siberia will be in the subtropics. The Mediterranean Sea will close, and in its place will be formed mountains comparable in height to the Himalayas. The next Pangea, Ultima, will be covered with 90% of desert. In the northwest and southeast of the continent, there will be giant mountain ranges. In other words, our planet will be somewhat similar to what it was about 335 million years ago. These processes do not stop, and we can observe this through earthquakes. Seismic events reflect the movement of plates relative to each other. You have probably already understood that today our planet is completely different from what it was at the time of Pangea. Nevertheless, researchers are convinced that the current appearance of the Earth will not last forever, and that in the future, a huge supercontinent like Pangea will reappear. Throughout the history of the Earth, continents have converged and diverged, sometimes forming supercontinents and then splitting again. So this will most likely happen again in the future. Already now, Australia is gradually approaching Asia, which actually indicates the possibility of the emergence of a future supercontinent in this area of the globe. How long will it take for such a massive landmass to form? A similar process can take 300 to 400 million years, and the same amount of time is needed for a supercontinent to split into several smaller landmasses. The Earth changes shape. It is not static. And if the contours of the continents and oceans that we are familiar with are represented on a globe, it does not mean that it has always been and will always be like this. And the modern appearance of the planet is only a temporary phenomenon. To date, scientists have developed a climatic habitability scale for the planet. According to this scale, the Earth is currently 85% habitable. This indicator does not include the territories of the Arctic region and Antarctica, where the average temperature is below 0 degrees Celsius. Scientists did not stop in their research and decided to determine the climatic conditions and population level of the planet on the new supercontinent that will form in the future. In case of the formation of the Pangea Ultima, the climate of the Earth will be completely different because all the continents will be united in the equatorial zone. The ice caps will remain only on the tops of the highest mountains, so that the sun will hardly be reflected in space. As a result, the average temperature on Earth will be similar to the Mesozoic period during the previous Pangea, and will be 20 degrees Celsius, or about 68 degrees Fahrenheit. In this respect, the level of habitability on the next supercontinent will be 99.8%. In addition, since most of the territories will be located in the equatorial and tropical climate zones, the biodiversity of the planet will also be exceptionally high. The current level of understanding of plate tectonics does not yet allow us to accurately predict what the new single continent will look like, but scientists no longer doubt that it will form in millions of years.